So, we looked at the amplitudes right in terms of this sum of forward going and backward going, right, voltage waves. Now, the question is, in the time domain we had something called the characteristic wave impedance. So, we will try to estimate what that is, right. So, if you remember one of the telegraph's equations, was this, right. So, we can try to find out the relationships between I plus, I minus, V plus and V minus, right, and the ratio of V plus to I plus or minus V minus and I minus is essentially what we called as characteristic impedance or Z naught, right. So, let us substitute these solution forms for the voltage and current and see if we can bring some relationships between the I plus I minus phasors to the V plus V minus phasors. Okay. So, dou V tilde by dou x is essentially V tilde plus, when I differentiate e to the minus gamma x with respect to x, I will have a minus gamma in the front, e to the minus gamma x plus gamma times V minus e to the plus gamma x is equal to minus of r plus j omega L times I plus e to the minus gamma x plus I minus e to the plus gamma x. Okay, do not forget that gamma squared was r plus j omega L times g plus j omega c. Okay, so when I look at this, I can compare this term to this term and I can get minus gamma V plus is minus r plus j omega L I plus, right. So, V plus by I plus is essentially r plus j omega L by gamma, which you can write as okay. Using this relationship, you can get that V plus by I plus phasor is essentially square root of r plus j omega L divided by g plus j omega c. Okay. So, similarly, you can also derive V minus by I minus with a minus sign is also is the same number, which we will call as the impedance. Right. So now the characteristic impedance is also a complex number, right? So r plus j omega divided by g plus j omega c is a complex number, right? So I'm hoping that you are comfortable with dealing with complex numbers, right? That you can do multiplications, divisions, right, and even square roots for complex numbers, right? I believe some of the scientific calculators can do this directly for you, right? But nevertheless, try to recap some of these basic analysis with complex numbers. I also find it beneficial if you go into the polar form, the square roots become just multiplying the exponent by half, right? So you can either take these rectangular forms for complex numbers, go into the polar form and then just do half, or you can do the direct square root of these as well. Just to do a quick check, remember that for lossless transmission lines, we had said that Z0 was square root of L by C, right? In the time domain analysis, we had said that the characteristic impedance Z0 was square root of L by C. Here also we can say that if R and G go to 0, we notice that the j omegas cancel and you get back the same expression. Right? Just sort of relating to whatever we have done, right? So by doing this single frequency analysis, we are trying to encompass the generalized distributed model, and we'd like to encompass even the real effects of having resistances and leakages between the conductors. But nevertheless, we also have to make sure that whatever we derive and we get is also applicable for the case when the transmission line is lossless, right? So whenever we get expressions, we can just do a quick check that we get back the same expressions that we got for lossless kind. Okay. So with these two relations derived, you can now say that I tilde is not really, there's not four different phasors, V plus, V minus, I plus and I minus. I plus and I minus can be derived from V plus and V minus, right, through Z0. So we can actually write I plus as V plus by Z0 e to the minus gamma x minus V minus by Z0 e to the plus gamma x. Okay. So in essence, we basically have V plus and V minus. Those are the two independent phasors that can only be determined based on the boundary conditions. What is the source? What is the amplitude of the sinusoidally fluctuating voltage source? What are the transmission line characteristics? What are the impedances? Those will essentially determine what V plus and V minus are going to be, right? For now, all we are saying is that for any transmission line in any scenario, for whatever be the load or source case, the voltage and the currents will have these kind of forms, right, where we are leaving the phasor V plus and V minus as generic phasors. But remember, they are constant complex numbers, right? They are not time varying or spatially varying. All the time and space variation has been absorbed in the e to the j omega t and the e to the minus gamma x, right? All right. So what did we do next? In the time domain analysis, we'll do the same thing. We'll kind of follow the same steps, right? So once we decided, we understood the transmission lines and how voltages and currents will have to behave in such a transmission line. We then went to putting the transmission line in a realistic circuit and then finding out what are the implications, right, of such a transmission line model in real circuit behavior, right. So we are saying that there is a sinusoidal generator with a series resistance Z0 which matches the Z0 of the transmission line, but we have a load ZL. This time ZL can be complex, right? Remember, this was one of the key advantages that single frequency analysis brought us, right. So we can actually have complex loads. So we'll say that ZL is a complex load, and we want to understand how the voltages reflect off of such a load in this generalized model. So this is where I think the textbook that we are referring to by Professor Shevgaonkar does a small change in variable, right. So he introduces a lowercase l, right, as the distance away from the load. Okay, so L equals 0 demarcates the location of the load itself, and as we move away from the load, L starts to increase. So remember that this was opposite to our conventional direction for x, right. So we do a transformation of variable where we want to go from x to L, right, and what we would have to do is replace x with minus L. So remember that if I go left, right, away from the load, L increases, but in the conventional direction for x, right, this would be in the negative x direction, right. So there is this subtle change of sign, right, that we are going to introduce. There is a reason to do so, right. So the main purpose of doing this is so that we are essentially trying to see how the load looks to the generator in steady state, right. So we will have to somehow transform this load impedance to what it looks like as a load impedance at the generator, right. So in order to do that, this kind of a transformation is beneficial. Okay. So if you remember from the time domain analysis, we had introduced the reflection coefficient gamma, which was V minus by V plus, right. So there it was a voltage at a particular location as a function of time, right. So at any instant of time, the reflection coefficient was V minus by V plus. Now we have to look at this reflection coefficient as a phasor, right. So we are now in the phasor domain where V plus and V minus are now complex phasors, right. So here we will say it is defined the same way but expressed with phasors. So remember, this was plus gamma x, which I am going to replace with minus L. Right. So at steady state, we will notice that the V plus and V minus phasors are changing. So at every location, I can define this ratio, right. So I can say that now gamma is a function of L. Okay. So we have a distance dependent reflection coefficient, right, which is defined as the ratio of V minus and V plus. can write this as V minus by V plus e to the minus 2 gamma L, and we'll call this gamma of 0, right? So gamma of 0 is the reflection coefficient at the load, right? So L equals 0. So if I were to know the V plus and V minus phasors at L equals 0 near the load, then I can get the ratio of the forward and backward propagating voltages at any position along the transmission line, and that will essentially now be length dependent, right? And the net voltage at any point along the line can always be written as V plus V minus right, and I can also write this as a function of gamma. Similarly, I right. So the reason I'm sort of writing these equations is to start getting used to writing voltages and currents in the phasor notation. We are sort of ignoring the time dependence, right? So we are not bringing the e to the j omega t explicitly each time. Remember that if you want to get to the voltages and currents, you always take the phasor form, which is only a function of distance multiplied by e to the j omega t, and then take the real part. Okay, so we are sort of saying that every point along the transmission line, the voltage or current will have a sinusoidal motion to it, right? And that in order to get the entire picture of this sinusoid, all I need to know is the amplitude of the sinusoid and the phase of the sinusoid with respect to the forcing function, which is the generator voltage. So we are just keeping track of the amplitude and phase changes. So if you wanted to say that I took 2 points along the transmission line and I asked what is the voltage waveform, you can say with respect to the generator voltage that the amplitude is multiplied by a prefactor so much, which is the magnitude of the V plus and the V minus, right? And then there is a phase term that adds to it, right? So phasors are just a way for us to keep track of both the amplitude and phase changes to voltages and currents that appear on the transmission line. So now we can say that the impedance at any position along the transmission line is actually changing, right? So even though it is ZL at L equals 0, as I move along the transmission line, the appearance of this impedance seems to have changed, right? So I'll try to give an intuition to this through some animations to the end of this week, but this is what the equations are telling us, right? So the amplitudes of oscillations for the voltages and currents are actually changing along the transmission line, just as we saw in the video for the beam bending, right? We noticed that there were locations where the beam bending was large, locations where the beam bending was small. So we are saying that the fluctuations in voltages and currents, the amplitude of these fluctuations is actually now is dependent on the location or the position along the transmission line, which means that the ratio of voltage to current along any point along the transmission line is actually changing, right? And if we can call that as the impedance at that particular location, V by I, we are actually noticing that we are actually getting different impedances at different points along the transmission line, right? Nevertheless, it's a periodic appearance, right? But we do notice that there is a change in the net impedance, right? This is like saying that the impedance at any particular location is basically voltage divided by current at that particular point, right? So if I had a probe that took any point along the transmission line and measured the voltage and current, you would say that this corresponds to an impedance of some Z, right? And the mathematics is telling us that because of these wave-like phenomena or wave-like behaviors for voltages and currents, and that these forward and backward propagating voltages constructively and destructively interfere with each other, we notice that the ratio of this voltage to current along the transmission line is now a function of where you are asking me to do this voltage to current ratio, right? So this is essentially the ratio of 1 and 2, equations 1 and 2, which should give me Z naught, right? So I'm just taking the phasor values for voltage and current, which are now length dependent, and evaluating the impedance, which is now a function of L, which turns out to be Z naught times, this is a minus here, right? So you can rearrange this and say that gamma of L is essentially Z as a function of L minus Z naught, right? So this is just a algebraic manipulation. You can go ahead. So which means to say that at gamma of 0 at the load, it's simply ZL minus Z naught by ZL plus Z naught, right? So this is conveniently the same expression we had got for resistive loads in the time domain analysis. We are just saying that it is, even though the impedance is complex, don't worry about it. You take the complex impedance, you subtract away the characteristic impedance of the transmission line, and then divide it by the sum of the complex impedance, the load impedance, and the characteristic impedance. So this ratio should give you the reflection coefficient, which is now a complex number at the load. And as I move away from the load all along the transmission line, I notice that this reflected wave sort of interfering with the transmitted wave from the generator is essentially constructively and destructively interfering along the transmission line to produce voltage over current ratios, which are now a position dependent quantity, which means to say that this impedance that was originally ZL at the location of where the load is connected to the transmission line is appearing as different loads as I move away from the load, right. So, that is a very key insight that we are getting, right. So, even though there is a fixed complex impedance that is connected to the end of the transmission line, depending on where I look along the transmission line and measure the voltage and currents locally at that point, I don't quite get the same voltage current relationships that I should observe for when I apply the voltage directly to the complex impedance, right. So, I actually get a different relationship between voltage and current along the transmission line, which is now spatially varying, right. So, this is something that we call impedance transformation, right. So, the impedance is a complex load ZL, but it is getting transformed to other loads Z as a function of L, right, depending on where you are looking along the transmission line in steady state. Okay. So, let us look at this impedance transformation a bit more closely, and we will derive a relationship so, from the last slide, we can say that the impedance at any location along the transmission line L is given by the characteristic impedance multiplied by right. So, this we got from the ratio of the voltage to current at any point along the transmission line, right. So, we can represent the reflection coefficient, which is the ratio of V minus to V plus at any point along the transmission line, to the reflection coefficient at the load, and then transform that reflection coefficient okay. Now, if we substitute for gamma of 0 being the ZL minus Z naught by ZL plus Z naught, this equation actually simplifies okay. So, please go back to the hyperbolic cosine and hyperbolic sine, right. Please recall that the expressions for cosine hyperbolic and sine hyperbolic. So, if you can use this relationship, so using 1 2 and the expression for sine hyperbolic as well. Right, you can actually arrive at this particular expression, right? So you replace for gamma 0 as ZL minus Z0 by ZL plus Z0, right? And then divide numerator and denominator by e to the minus gamma L, so that you get an expression that closely resembles, right, your cosine hyperbolic and sine hyperbolic. You can collect all those terms together and you can arrive at this expression, right? So sometimes we can also normalize, right, this impedance transformed impedance to the characteristic impedance, right, and call this the normalized right, and this is indicated with a bar on the top, right, and we can write this as right. So I'm just introducing normalized impedance as a concept. It's just the ratio of whatever impedance you're looking at to the characteristic impedance of the transmission line, right? It's oftentimes beneficial to not look at complex loads in and of itself, right, but rather in relation to characteristic impedance, right? So remember that in the time domain analysis, when we had a few lectures on trying to get the intuition to the transient behaviors in time domain, I suggested that we look at impedances that were either larger or smaller than the characteristic impedance, right? So in some sense, the characteristic impedance of the transmission line sets the reference to all the impedances of interest, right, that is connected to this particular circuit. So it's always good to sort of think of impedances with reference to the characteristic impedance, which is why we introduce this normalized impedance, right? So even when we go to the analysis of looking at understanding Smith charts, we will introduce the concept of normalized impedance and use it there, right? Okay, so all this mathematics is essentially trying to portray the fact that the sinusoidal excitations of voltages that are excited at one end of the transmission line propagates in a wave-like form, just as you saw in the case of the beam bendings moving towards the end of the line, right? You find these sinusoidally varying voltages propagating along the transmission line, reaching the load impedance ZL, getting reflected, say some portion of it is reflected when ZL is not matched to Z0. So some portion of those sinusoidal wavy forms are coming back to the generator, and the combination of these forward going voltage waves and the reverse going voltage waves create some sort of an interference phenomena, which shows us that at different positions along the transmission line we notice variation in voltages and currents, right? The amplitude of the voltage fluctuations and current fluctuations are now a position dependent quantity, which appears as though if I were to just locally measure the voltages and currents, it corresponds to a particular load that is not the same as the load that is connected at the end of the transmission line, but a different load, right? And this different load is what we call as the transformation, right? So the load impedance has transformed and made itself look like a different impedance depending on where you are looking at along the transmission line, right? So all this transformation in impedance fundamentally lies in the idea of constructive and destructive interferences formed by forward propagating and reverse propagating voltages, right? So this is just a small remark, right? So when we say that the end of the transmission line where the load is connected as L equal to 0, it is nothing special, right? It is but a reference. It's like saying that my origin of my XYZ axis starts here, right? So there's nothing really special about the L equals 0 point. It is but a safe choice of origin so that we can relate to the reflection coefficients and the impedances to what we find at the load, right? So